Dreams are not a random byproduct of sleep. They are biologically orchestrated phenomena that serve specific purposes in how we encode, reorganize, and discard information. From a neuroscience standpoint, dreaming is intimately connected to the activity of specific brain structures and neurochemicals during distinct stages of sleep. To understand how this works, we must first break down what happens to the brain as we sleep, especially during REM, rapid eye movement, and non-REM sleep, because both stages play different roles in cognition and emotional regulation. Non-REM sleep typically dominates the first part of the night and is characterized by slow wave activity in the brain. During this time, the hippocampus, our brain's temporary storage system, communicates actively with the neocortex, which is the long-term storage site. This is when factual memory consolidation begins. However, as we transition into REM sleep, which becomes more frequent and prolonged in the later stages of the night, the brain enters a neurochemical state dominated by acetylcholine with suppressed levels of norepinephrine. This shift is critical because it allows for a loosening of logical constraints and fosters creativity and associative thinking. The prefrontal cortex, responsible for rational thought and executive control, goes mostly offline during REM, while the limbic system, including the amygdala, becomes more active. That's why dreams often feel emotionally charged and sometimes bizarre in structure. The visual areas of the brain, especially the occipital cortex, remain highly active during REM. This explains the rich imagery often associated with dreams. Meanwhile, the dorsolateral prefrontal cortex, which normally evaluates reality and helps us plan, is less active. This diminished rational oversight enables the brain to explore thoughts and scenarios outside the bounds of waking logic. Interestingly, this freedom is not without purpose. The brain is replaying, reactivating, and recombining neural patterns from recent experiences and older memories. This process isn't merely entertainment, it's deeply functional. From a neurobiological perspective, dreams serve to integrate newly acquired information with prior knowledge and emotional frameworks. This is a form of memory triage, where the brain decides what information to retain, what to modify, and what to discard. During REM sleep, theta oscillations which originate from the hippocampus facilitate this coordination. These brain waves essentially act as timing signals, enabling neurons to replay specific memory traces while simultaneously integrating them with networks in the cortex. It's like editing a movie. Certain scenes are emphasized, others are cut, and transitions are added to improve the overall narrative coherence. Dreaming also enables what's known as synaptic homeostasis. Throughout the day, our brain forms countless new synaptic connections, many of which are redundant or unnecessary. During sleep, particularly during non-REM and REM cycles, the brain undergoes a process of synaptic downscaling. This means weaker, less relevant synaptic connections are pruned, and stronger, more useful ones are stabilized. Dreams accompany this process, often as a byproduct of the brain reactivating and testing different patterns of neural activity. If a certain pathway is deemed unhelpful, it's less likely to be reinforced in future sleep cycles. Thus, dreams contribute to a biological version of defragmenting our mental hard drive. One of the most fascinating elements in dream neuroscience is the concept of offline processing. When we sleep, the brain is still working, just not on immediate external tasks. It is instead integrating new learnings, processing emotional events, and simulating potential futures. For instance, the default mode network, which is involved in introspection and mind wandering during wakefulness, is active during REM sleep. This is why dreams often involve scenarios that are not real but symbolically meaningful. The brain uses these simulated environments to test out reactions, rehearse possible challenges, and resolve internal conflicts. The absence of external sensory input during sleep makes this a purely internal process, and dreams are the experiential outcome. Even more intriguing is how neuromodulators govern the dreaming brain. During waking hours, we operate in a neurochemical state rich in dopamine, norepinephrine, and serotonin. These neurotransmitters are crucial for focus, motivation, and emotional stability. In REM sleep, however, norepinephrine plummets. This absence allows the brain to revisit emotionally intense experiences without triggering the same level of stress. It essentially creates a safe space for emotional reprocessing. That's one reason why people often report dreaming about events that were emotionally unresolved during the day. The brain revisits them not to relive the trauma, but to process it in a less aroused state. Current research even suggests that people who get sufficient REM sleep have improved emotional regulation, better memory recall, and higher levels of creativity. PET scans show that after a night of sufficient REM sleep, the connectivity between the prefrontal cortex and the amygdala, the brain's emotional response center, is stronger. This means people are better able to regulate emotional reactions. In contrast, sleep deprivation, especially REM sleep deprivation, leads to increased amygdalar reactivity and decreased logical oversight. The takeaway here is that dreams do more than entertain. They calibrate our brain's response to reality. Understanding the neuroscience of dreaming invites us to view our sleep not as wasted time, but as an active, biologically optimized state for learning, unlearning, adapting, and rebalancing. Dreaming is a key pillar in that process. And the more we understand how the brain dreams, the more we can leverage sleep to fine-tune our learning, mental health, and performance. Dreams play a vital and often underestimated role in memory consolidation. When we learn something new, whether it's a skill, a fact, or an emotional experience, that information is initially stored in a fragile, unstable form. Throughout the day, it resides in temporary networks like the hippocampus, which acts like a short-term hard drive. But for that memory to become stable, retrievable, and embedded in long-term storage, it must undergo a process called systems consolidation. This is where dreams come into play, particularly during specific stages of sleep, like REM and non-REM cycles. The brain doesn't just passively record experiences. It actively reprocesses them, evaluates their relevance, and integrates them into broader networks of meaning. And it often does this through the medium of dreaming. Memory consolidation during sleep is not just about repetition or simple review. It's about selective strengthening. The brain evaluates the emotional salience, novelty, and utility of the information it received during wakefulness. Research shows that emotional memories are more likely to be replayed during REM sleep. This is due in part to the increased activity in the amygdala and hippocampus, two key regions involved in emotional memory and spatial/contextual memory, respectively. During REM, the neurochemical environment characterized by high acetylcholine and low norepinephrine allows neurons to fire in flexible, less rigid ways. This neuroplasticity supports the replay and strengthening of emotionally meaningful or goal-relevant experiences. In other words, we don't just consolidate any information. We consolidate what matters most to our survival, goals, and emotional well-being. This dream-related replay is not a literal one. You don't relive the day's events like a video recording. Instead, the brain extracts the key elements, the patterns, themes, and associations, and reweaves them into dream scenarios that often feel symbolic or surreal. For example, you might dream of taking an exam after spending the day learning a new skill or rehearsing a presentation. But instead of the exact task, the dream presents a metaphor like being on stage or navigating a maze. These scenarios are not random. They represent how the brain is actively reorganizing and linking new information with existing memory networks. This associative processing allows the brain to generalize knowledge, draw new inferences, and connect dots that weren't obvious during conscious thought. The hippocampal, neocortical dialogue that takes place during sleep is especially critical. During non-REM sleep, slow oscillations and sleep spindles facilitate the transfer of memory traces from the hippocampus to the neocortex, where long-term storage occurs. This process is thought to be a major component of declarative memory consolidation, facts, knowledge, and events. Then, during REM sleep, those same memory traces are reactivated in a different neurochemical context, allowing them to become more flexible, creatively integrated, and emotionally neutralized. This means the dream serves both a stabilizing and an adaptive function. In addition to consolidating factual knowledge, dreams are also heavily involved in procedural learning, skills, habits, and motor sequences. Studies using tasks like mirror tracing or keyboard sequences have shown that participants who dream about the task perform better the next day than those who do not. The dreams don't need to be accurate representations of the task. Even symbolic or distorted dream versions correlate with performance improvements. This suggests that the brain is simulating, rehearsing, and embedding skill-related neural pathways during sleep, again using dreams as the experiential surface of that activity. Another critical function of dreams in memory consolidation is emotional memory processing. Imagine someone has a painful breakup or experiences a stressful conflict. If that event is deeply emotionally charged, it risks overwhelming the nervous system. But during REM sleep, when norepinephrine levels drop, the brain is able to revisit these memories in a way that blunts the emotional charge while retaining the narrative. This is sometimes referred to as overnight therapy. The dream might involve strange or fantastical versions of the real event, but what's happening underneath is very real, emotional decoupling. The emotional tone becomes muted while the core memory is preserved. Over time, this allows the individual to remember the event without being hijacked by the emotional pain, enabling resilience and learning. Dreams also help create what psychologists call schematic mental frameworks that allow us to categorize and navigate new experiences more effectively. By replaying and recombining past experiences during dreams, the brain constructs general rules and templates for future behavior. For example, if you've had multiple experiences speaking in front of people, your dreams might integrate these into a unified memory trace that helps you develop confidence or anticipation strategies, even though each specific dream scene differs. Interestingly, sleep studies using EEG and fMRI have shown that the more vivid or frequent one's dreams are, particularly dreams that are emotionally or thematically connected to date experiences, the greater the benefits in memory retention and problem solving. This has led to increased interest in dream journaling and intentional dream incubation as tools to enhance learning. By setting an intention before sleep, such as reviewing a concept or posing a question, and then reflecting on your dreams upon waking, you can help the brain prioritize and reinforce specific types of memory consolidation. In essence, dreams act as an intelligent filter. They don't just reflect what we've been through. They decide what to keep, how to connect it, and where to store it. Dreaming allows for integration across different brain systems: emotional, cognitive, motor, and perceptual. And this integration is not random. It's guided by neurochemical states, prior knowledge, and evolutionary priorities. So when we say sleep on it, we're actually invoking one of the most powerful cognitive tools available to the human brain, dream, facilitated consolidation. Understanding this process allows us to better respect and optimize our sleep cycles, not just for rest, but for insight, learning, and long-term adaptation. Forgetting is not a flaw of the brain. It's an essential feature. Without the ability to forget, we would be overwhelmed by an endless stream of sensory inputs, irrelevant facts, and emotional noise. The human brain, particularly during sleep, engages in a highly intelligent form of active forgetting, and dreams are at the center of this function. Most people associate dreams with memory, creativity, or insight, but what often goes unnoticed is that dreaming is also how the brain prunes, deletes, and reorganizes memory traces that are no longer valuable or relevant. Forgetting, especially the kind facilitated through dreaming, is not simply about loss. It is about adaptation. It allows the brain to create space, maintain flexibility, and prioritize what truly matters for future behavior and survival. Neuroscientists now understand that the brain operates with limited representational capacity. There is a ceiling to how much information can be maintained in a usable, accessible form. Throughout the day, our brain forms thousands of new synaptic connections in response to experience. But not all of these connections are beneficial. Some are noisy, redundant, or conflicting. If these are not filtered out, the neural networks that underlie attention, decision, making, and learning become cluttered and inefficient. This is where dreaming steps in, particularly during REM sleep. During this phase, the brain enters a state that favors the weakening of unnecessary or low-value synapses, a process known as synaptic downscaling. Synaptic downscaling is governed by specific molecular and electrical mechanisms. The neurons that are less frequently activated or less synchronized with meaningful activity tend to lose their strength, while those that are repeatedly engaged or strongly associated with goal-relevant behaviors are preserved. Dreaming, especially the non-linear, emotionally charged, and metaphorical nature of REM dreams, helps the brain test and evaluate these connections in a safe, simulated environment. If certain patterns are no longer useful, such as those tied to outdated fears, irrelevant routines, or minor observations, they are marked for deactivation. This process is supported by the unique neurochemical landscape of REM sleep. In waking states, neurotransmitters like norepinephrine and serotonin help the brain prioritize vigilance, attention, and detailed encoding of information. But during REM, norepinephrine levels drop to nearly zero. This neurochemical silence creates an ideal environment for reprocessing without heightened emotional arousal. It enables the brain to re-experience events with emotional detachment, allowing it to determine which connections are still useful and which can be safely forgotten. Interestingly, this type of forgetting is not just passive fading, it's an active recalibration. For instance, when a person is exposed to repetitive stress or unhelpful behavior patterns, the brain may initially encode them strongly due to emotional salience. But over time, if these experiences no longer align with the person's goals or environment, the brain can begin to weaken their impact through dream processing. In fact, this might explain why, after repeated dreams or after a good night's sleep, a previously intense memory feels dull or even irrelevant. The dream didn't just help you make sense of the event. It helped you let go of its control over your internal narrative. This also relates to the concept of emotional unlearning. Some studies suggest that dreams play a role in helping us decouple conditioned responses like fear or anxiety from neutral stimuli. For example, someone who has a panic response to social situations might find over time that this fear lessens, even if nothing has changed in their waking strategy. What may have changed is how their brain reprocessed those social scenarios during REM dreams. The lack of norepinephrine and the dominance of acetylcholine create conditions under which fear responses can be replayed but not re-encoded. This weakens the original emotional association and contributes to psychological flexibility. There is also evidence from computational neuroscience suggesting that the brain uses dreaming to prevent overfitting. much like artificial intelligence models that become too specialized and lose generalization. If the brain were to retain every detail of every experience, it would become too rigid and fail to adapt to new situations. Dreams allow the brain to abstract away from specifics and retain general principles or patterns. This is why you may remember the lesson or emotional resolution of a dream without remembering its exact content. The unneeded details are dropped and the essence is retained. Sleep experiments in both humans and animals have shown that dreams often include distortions, dislocations, or bizarre combinations of real-world events. Far from being meaningless, these distortions help the brain break rigid associations and reformulate more adaptive or flexible interpretations. For example, dreaming about a school exam in a jungle or a family member flying may seem nonsensical, but they serve to repackage emotional memories in ways that allow for detachment and selective forgetting. The dream creates novelty, which is a critical driver of neuroplastic change. This novelty helps loosen the grip of stale or redundant memory circuits. Moreover, not all forgetting is equal. The brain is selective, and dreams often prioritize forgetting low-impact memories. This supports a cleanup operation that maintains efficiency. You're less likely to remember what color shirt someone was wearing yesterday unless it had emotional or personal significance. Dreaming helps maintain that filter. It's not about removing memory randomly. It's about prioritizing what contributes to adaptive behavior and what doesn't. In sum, dreams serve as an intelligent sorting mechanism. They help consolidate what matters and actively eliminate what doesn't. They free the brain from being bound to outdated fears, habits, or trivial details. This function of forgetting is essential for clarity, creativity, and growth. The paradox is that through dreams which feel vivid, emotional, and sometimes intense, the brain accomplishes one of its quietest and most invisible tasks, the art of letting go. Understanding this process doesn't just change how we think about sleep. It changes how we think about change itself. Lucid dreaming is a fascinating neurological phenomenon where an individual becomes aware that they are dreaming while still in the dream. Unlike typical dreams, which occur without conscious oversight, lucid dreams represent a hybrid state where aspects of wakefulness, like self-awareness and volitional control, are integrated into REM sleep. From a neuroscience perspective, lucid dreaming activates brain regions that are usually dormant during REM sleep, particularly the dorsolateral prefrontal cortex, which governs logical reasoning, planning, and metacognition. This reactivation of executive functions allows the dreamer to observe, influence, and sometimes completely direct the content of the dream in real time. But the implications go far beyond novelty or entertainment. Lucid dreaming offers a powerful gateway into harnessing neuroplasticity, the brain's ability to rewire itself based on experience, intention, and mental rehearsal. Neuroplasticity is typically thought of in terms of practice, repetition, and behavioral engagement. However, research increasingly shows that mental simulation, especially in a vivid and immersive environment like a lucid dream, can also reinforce neural circuits associated with skills, habits, and emotional responses. In lucid dreams, the brain is generating a highly realistic virtual world, complete with sensory experiences, emotional tones, and cognitive engagement. This simulation involves the same neural substrates that are active during real-world experiences. For instance, if you practice a motor skill like playing the piano or shooting a basketball in a lucid dream, the motor cortex, basal ganglia, and cerebellum show activation patterns remarkably similar to waking performance. This suggests that the brain does not entirely differentiate between imagined and real movement, particularly when the imagined scenario is vivid, emotionally engaging, and repetitive, all of which are qualities present in lucid dreams. What makes lucid dreaming especially valuable for learning is the ability to repeat and refine behaviors without physical fatigue, environmental distractions, or real-world consequences. An athlete could rehearse a sequence of movements. A speaker could practice presenting to a crowd. Even someone with social anxiety could simulate a feared interaction to reduce its emotional charge. These rehearsals are not merely theoretical, they trigger synaptic strengthening, reinforce neural firing patterns, and enhance procedural memory. Some studies show measurable improvements in waking performance after repeated lucid dream practice. This is because the neural networks being engaged are not imaginary. They are real pathways, and activating them, even in sleep, enhances their efficiency and accessibility. Lucid dreaming also enables emotional rewiring. Because the brain is in a neurochemical state with low norepinephrine, it allows for reprocessing of emotionally charged content in a calmer context. When someone becomes lucid in a dream involving fear, shame, or trauma, they can consciously choose a new reaction, reframe the narrative, or even alter the dream environment. This creates a feedback loop in which the dreamer not only re-experiences the emotion, but also regulates it with new internal responses. Over time, this leads to a shift in how the emotional memory is stored and how it influences waking behavior. In therapeutic contexts, this has significant implications for treating nightmares, phobias, and PTSD. By transforming the response within the dream, the person rewires their brain's conditioned associations. Lucid dreaming also fosters creativity by allowing conscious exploration of unconscious material. Because the dreamer retains some executive control, they can direct the dream toward problem-solving, visualization, or inspiration. Numerous artists, scientists, and inventors have used dreams, lucid or otherwise, as a creative tool. In lucid dreams, one can intentionally ask a question, design an experiment, or test a concept within the dream itself. The freedom from waking logic combined with the conscious mind's ability to observe and influence the scenario produces a state highly conducive to novel connections and insight generation. This is a form of enhanced associative processing, where ideas from disparate domains can be fused in new, surprising ways. From a brain chemistry standpoint, the unique balance of acetylcholine, dopamine, and reduced serotonin creates the perfect environment for both creativity and emotional plasticity. Acetylcholine facilitates memory consolidation and cortical communication. Dopamine enhances motivation, goal, direction, and internal reward signaling. In lucid dreams, this dopaminergic activity is heightened, which is why the dreams often feel euphoric or empowering. This biochemical landscape allows the brain not only to simulate experience, but to encode it with a high degree of emotional salience, increasing the likelihood that the insights gained during lucid dreaming will transfer into waking awareness. Training oneself to lucid dream is a skill that can be learned, and doing so involves developing metacognitive awareness during the day. Techniques such as reality testing, where you periodically ask yourself if you're dreaming, and keeping a detailed dream journal increase the chances of recognizing when you are in a dream state. Once that recognition occurs, the next step is to remain calm, stabilize the dream, and set an intention. These intentions could range from practicing a skill to resolving an internal conflict, or simply observing the subconscious in action. The more frequently one engages in lucid dreaming, the more skilled they become at entering and utilizing that state deliberately. Lucid dreaming is not just a curiosity, it is a window into the malleability of the human brain. By consciously engaging in dreams, we can tap into neuroplastic processes that are usually passive or unconscious. This includes not only reinforcing new learning and improving skill acquisition, but also reshaping emotional reactions, boosting creativity, and exploring the deeper architecture of thought. With the right protocols and mental training, lucid dreams can become a powerful laboratory for cognitive and emotional transformation. They allow us to step into a virtual version of ourselves, experiment with new behaviors and identities, and bring those discoveries back into waking life where real change begins.